Right. So how are you guys today?
Fine, right.
Right. So I hope everyone is great. Okay. So before we start our lab today, I'm going to first continue with the yesterday's lecture, which was about the rotation on rigid bodies or rotation dynamics. Okay. So basically, yesterday we have discussed about angles. All right. So how we define 1 radian, okay, where we have the sector is equals to the radius of the circle, and then we also define the angular velocity, right? So where we have the axis of rotation at the center of that circle, all right? And today we're going to define the next term, which is the angular acceleration. Okay, all right, so what is angular acceleration? So basically, yesterday we learned about the angular velocity, all right? So basically, it is actually the difference of angular velocity divided with time, right? So it is actually, if you want to find the angular acceleration, okay, if you are given, if you are given the angular acceleration, then you want to find the angular velocity. So what do you do is you need to do differentiation, right? So you differentiate that and then you obtain the angular velocity. But if you want to find the angular acceleration from the angular velocity, so you just divide that with the time taken. All right. So okay, so basically it is the same concept, okay, as the angular velocity. So except that we use the angular velocity rather than we use the, okay, angle, the difference of angle. So you need to remember that. So the two different things, okay, we have one angular acceleration and angular velocity. So angular velocity depends on the angle and angular acceleration depends on the angular velocity. Okay, all right, the direction of the angular acceleration and the angular velocity. So where here we have alpha, alpha is the angular acceleration, and omega, omega is the angular velocity. All right, so they are, if they are in a similar direction, okay, the rotation is speeding up. Okay, so it is like velocity and acceleration. Okay, so when the, for example, when the car is speeding up, all right, so of course the acceleration increase. So when the acceleration increase, so the direction of the acceleration will be similar to the direction of the velocity. Okay, however, all right, it will be opposite when the rotation slowing down. Okay, so we have the rotation, the rotated object. Okay, for example, this one. All right, so for example, like in the picture, so we have this object rotated on the counterclockwise, all right, and then it slows down. When it slows down, the angular acceleration will be negative, right? But the omega, all right, which is the angular velocity, is still positive during that time because it is still having the speed. Okay, so that's the difference of the when the angular acceleration will be positive and when the angular acceleration will be negative or opposite to the angular velocity. Okay, so we still use much more similar equation that we use for the linear acceleration. Okay, for example here, okay, we have previously we have Vx equals to V naught x, so which is the initial velocity plus axt. Okay, so over here we have also similar where we just replace Vx with omega, right? So over here we use omega z. Okay, so why z? Okay, because we consider the axis of the rotation. Okay, so as you remember, we use the right hand rule to define the axis, whether it is out of page or inside of the page or to the left or to the right. Okay, so we have omega z equals to omega naught z plus alpha z t. Okay, and then we also have x. Okay, in the linear acceleration we have x, so where x equals to x naught plus v naught x t plus half ax e squared. All right, so now we replace that x with theta, which is the angle. So before this it is the displacement or distance, now we use the angle. Okay, so theta equals to theta naught plus theta naught z t plus half alpha z t squared. Okay, so for the rest is actually the similar equation, similar equations. We just, what you need to just remember is we replace, okay, omega with v, and we replace theta with x, okay, in the previous equation. Okay, let's have a look at one example over here.
In example 9.3, a Blu-ray disc is moving with an initial angular velocity of 27.5 radians per second, t equals 0. However, it has a constant acceleration of minus 10 radians per second squared, as shown in this diagram. A line is drawn between points P and Q such that it lies on the positive x-axis at t equals 0. We'd like to find its angular velocity at t equals 0.3 seconds, and the angle that this line makes at that time after it has rotated some. So we're going to look for this angle here, theta. This is clearly a rotational kinematics problem, and here's our toolkit for looking at rotational kinematics, where we're going to assume that the angular acceleration is constant. The angular velocity is given as a function of time in this equation, and here's the angular displacement as a function of time. And this equation relates the angular velocity to the displacement where time is not involved. So we're going to use a couple of these equations for the solution. Here's our parameters. The initial velocity is 27.5 radians per second. We'll take our initial angle as 0, and of course the angular acceleration is minus 10 radians per second squared. Plugging into this equation, we can find the angular velocity after 0.3 seconds has passed, and it's going to be 0. For part B, we're going to use this equation, where theta naught, of course, is going to be 0. And this is the initial angular velocity, and here's the angular acceleration. And again, we put in 0.3 seconds into this equation. We find that's 7.8 radians, which corresponds to 1.24 revolutions. So basically, in 0.3 seconds, this line goes around 1 full revolution, and then about 1/4 more. So the line is pointed up somewhere here. And this ends at 9.3.
Okay, so The problem is actually is
Example
about the
9.3. A Blu-ray disc is measured
Blu-ray
at
disc.
80%.
All right.
A line
So
is
this is a
drawn on
CD.
the x-axis.
Okay, and then this angular velocity, okay, at t equals to 0. So initially, at t equals to 0 is 27.5 radian per second. Okay, so that's the omega. All right, and then its angular acceleration is constant. Okay, at negative 10 radian per second squared. A line PQ. Okay, we have the line PQ on the disk. Okay, surface lies along the positive x-axis. So it is on the horizontal direction at t0. Okay, so the first question is, what is the this angular velocity at t is 0.3? So meaning that now you have at t0. So what is it at t 0.3? So it moved a little bit. Okay, so how do we solve that? So we use the equation that we just learned, right? So what do we have? So first we need to find out what is the equation that is related to the angular velocity and the angular acceleration, because you were given with that values, right? And then you also have the time. Remember that you have the initial time and the current time, right? So actually you need to look at the equation that having t and also t naught, all right? T and also t naught. All right. So because we want to know, or because we want to know that what is the angular velocity, all right? So we need to find out the angular velocity, and then we have the initial angular velocity equation, all right? That is omega z and omega naught z. Okay, so as defined here, so we have omega z equals to omega naught z plus alpha zt, right? So we know that. So we have omega naught z, and then we have alpha z. And do we have the time? Yes, we have the time. So we can solve that, right? Okay. So by using that equation, so we can solve that. Okay. So that one is simple. All right. So we can just use the first equation there. And then B. All right. What angle does the line PQ makes with the positive x-axis at this time? Okay. So we want to know. Okay. Now we already have the time. Okay. We already have the angular velocity, right, at t point 3. Okay. And then we want to know the angle. So we need to find out the equation that having the angle on that. All right. So we look there. So we have the second equation. Okay. So second equation. So what do we have? Okay. So theta naught, of course, we have it as 0, right? Because uh, it lies on the positive x-axis, right? And then omega naught z and t, we also have that. Okay. So we have all of the information here, right? We have all of the information here. Also use the equation number 4 as well. So it doesn't matter which equation that you want to use, because now you have all of the information. All right. So basically, if you use the second equation,
To use seconds into this equation.
okay.
We
So
find
basically, you just need to replace that. Okay. So finally, what you obtain theta is 7.8 radian. Or if you convert that to the revolution, it is 1.24. Okay, to convert to revolution, you just divide. You just divide with the 2 pi. Okay. Right, so let's continue. Okay, so right. So how do you want to relate the linear and angular kinematics? Okay, so we have the linear motion as we learned in the chapter 1, chapter 2, right? So we have the linear motion, and then now we have the angular motion, all right? So a point at a distance r, okay, from the axis of rotation as the linear speed of v equals to r omega, okay? So what do we have there? So the distance which point P on the body moves, so we have the theta, right? And then we have the linear speed of point P. So point P is traveling at a linear speed, so which is V, right? So V that is equals to R omega. Okay, so omega is the angular velocity, all right, and R is the radius. So of course, we have increasing of the V, okay, which depends on the omega. So you note that. So V is the linear motion, right? So that is the multiplication of R with omega, the angular velocity. Okay, so for a point at a distance r from the axis of rotation, so we have a initial acceleration. Okay, so before that we already defined the velocity. Okay, now we want to define the tangential acceleration. Then the tangential acceleration is r, okay, r alpha, okay, where alpha is the angular acceleration. So it is actually simple as that. So we just replace, okay, omega with alpha, all right, and then we can calculate the uh, tangential acceleration. Okay, so meaning that the direction of the acceleration will be tangential to the point on that circle. All right, as you can see from the figure here, okay, like this one. Okay, and then if we want to find, because um, the as we learn, right? As we learn, when the object moves, okay, so when the object moves in a circle, right? As we learn in chapter 2, chapter 3, right? So what we learned there, that the actually the acceleration is point into the center of the circle, okay? So that is the the radial acceleration, okay, radial acceleration, or we also call that as the centripetal acceleration. So we call that also as the centripetal acceleration. Okay, so that centripetal acceleration is actually, okay, perpendicular. So you know that it is perpendicular to the point on that circle. All right, so it is perpendicular to the point on that circle. So how do we calculate that? The a, right? So a, right, is equals to v squared. All right, so v squared, so which v, okay, we obtain before that, it is r, okay, it is r omega, right? So v is r omega. So what do we have there? All right, so we have over here we have v squared over r. Okay, so now the a radian is r omega, should be r omega squared over here. Okay, so it should be r omega squared. Okay, because we replace v, so v is r omega. So when we square that, okay, so we have r squared omega squared. So we divide that with r. So we have R omega squared. So for the A rep. Okay. So once you obtain that, it is actually you can obtain your linear acceleration, okay, at a point P. So because you have that component A tangential and A radiant. Okay. So what is your the linear acceleration at that point P? So for example, like this one. So at this point, so it is actually the square root of R alpha squared plus omega squared R squared. Okay, so that is equals to your A. Okay, which is your linear acceleration at that point P. Okay, so you need to solve this. Okay, so if you want to find this angle, so how about the angle that is made between that? So it is actually the angle. Let's say it is phi. So let's say it is phi. That is equals to the tangent. Sorry, it is inverse tangent of R omega divide. Sorry, it is R alpha divide with omega squared R. Okay, so it is actually inverse tangent of alpha divide with omega squared. Okay, do you get that? Any questions so far? All right, so hope you are clear with the concept of having acceleration, okay, on the uh, angular acceleration and angular velocity. Okay. All right. So the importance of using radian. So why we use radian? Okay. So we must always use radian when relate with the linear and angular velocity. Okay. So let's say over here, so we have theta as 60 degree. So degree is not in the radian. So we must convert that to the radian. Okay. So how to convert that to radian? So you remember the rule. So 180 degree is pi radian. Okay. So it is actually pi equals to 180. So if it is 60, so 60 over 180 times pi. So you get that angle of 60 degree in terms of radian. Okay. So it is basically so pi over 3 radian. So 460 over 180 degree. Okay, so you must state that. All right. So over here, if you want to define the S, so because S equals to R theta, so we must define this theta in terms of pi radian. So we cannot define that in terms of the degree. Okay. So just to note that. Okay, now we have the concept of rotational kinetic energy. Okay, so the rotational kinetic energy is given by K, and then it is equals to half I omega squared. So now we have the term I. So what is I? So I is the moment of inertia. Okay, so how do we obtain I? Right? To obtain I, we need to multiply that with the mass of the particle involved, okay, by the square of the distance, okay, the distance of the rotation, okay. So from the center of the object, okay. So it is like a radius, okay. So you are given with this equation actually, okay, m r squared. Okay, if you just only have one, then I equals to m r squared. Okay, but if you have multiple rotational bodies, all right, so you have multiple rotational bodies, let's say you have four, then you need to sum all of that, and then you obtain the moment of inertia for the uh, for the object, okay. And then the unit of I is in terms of kilogram meter square. Okay, we want to look closer on the moment of inertia. Okay, for example, we have an apparatus free to rotate around a vertical axis. Okay, so you just rotate that. Let's say it is like your tap. Okay, your tap in your tap water. All right, at your house. So you do the rotation. So it is a vertical axis. Okay, so it rotates on the vertical axis. So we want, if you want to reduce the moment of inertia I, okay, we lock the two equal mass cylinders, right, close to the center of the horizontal shaft, right? So let's say over here, okay, meaning that moment of inertia. So inertia is like uh, something that is actually just before we start the just before we start the velocity, all right, so we have a moment of inertia before it moves, all right, before it moves we have that inertia, okay. So inertia is like what we call that, maybe you can consider that like a friction, okay, that actually hesitate, okay, to remove to start moving the object, okay. So that's basically the inertia. Okay, so we want to reduce that. So for example here, so initially, let's say we have the bar over here. So initially the bar is over there. Okay, the bar is over there. Okay, so we move that to the center of that, okay, which is closer to the axis of rotation. Okay, center of axis of rotation. So what happened? What happened when you have that? Okay, of course, you can now turn that more easily. So you can turn that more easily. Okay, it is like if you have a, let's say if you have a fan, right? If you have a fan, okay, let's say you put that on that fan. So on the shaft of that fan, for example, like that. Okay, you put some object over here. Okay, you put some object over here, and then of course you feel heavy to rotate that. Okay, but if you move this object to that center, okay, to the center of the rotation, so you move that, of course you feel it easier, okay, to move that, okay. Okay, so basically that's why you have the big bulky thing, all right, on that. Let's say this is on the stand fan, all right. So the motor, all right, it is located somewhere around here. Okay, so it is not been designed, okay, to be put at that outer part of that fan. Okay, so because you will have less moment of inertia to move the object. Okay, if you want to increase, right, so as I just mentioned, so when we have when the bar, okay, when this two bar is actually at the end of this shaft, right, then of course the moment of inertia will increase. So it is harder, okay, harder for the apparatus to start rotating. Okay, so you want to push it, so you feel it a bit heavy. Okay, so in the real world, so we have the moment of inertia in the bird's wing. Okay, so when the bird flaps its wings, okay, it rotates the wings up, okay, and down the shoulder. Okay, a hummingbird has small wings with a small moment of inertia. Okay, so the bird can move its wings rapidly, okay, at 70 beats per second. Okay, so inversely, we have the Indian condor, a bird, all right. So this black one, so it is like an eagle, all right, has immense wing with a large moment of inertia, okay, and flaps its wings about 1 beat per second. Okay, so you can see that the difference. Okay, so because it is actually heavier to that side, all right, so it has a larger moment of inertia. Okay, compared to this bird, all right, hummingbird have smaller moment of inertia. Okay, so what can you think about? What's the difference between this? So this is a big bird and then this is a small bird. Okay, so how do you read that with the physics quantity about the moment of inertia? Of course, so you have a bigger mass, all right? So you have a bigger mass on this bird, okay, compared to this bird, okay? So when the mass is small, of course, your moment of inertia is smaller. Okay, so we look some other example. All right, so we have for example, we have this object, the slender rod. So we have the axis to center. So the moment of inertia of this object is 112. Okay, 112 m l squared. So m is the mass of this object. Okay, okay, and then you look at, so you look at here. So the axis is through the center. Okay, the axis of that is through the center. Okay, so it is 112. Okay, and L squared. So L is the length of the object. Okay, and then we have another similar center rod, but if the axis of the rotation is over here, okay, of course, okay, when you have, I say, I have this pen, okay, and I want to move it, okay, at this edge, okay, you notice that it is harder, right, to move compared to if I put my hand over here at the center. Okay, if I put my hand at the center of this pen, it is easier to rotate that compared to if I put my hand, right? If I put my hand at the edge, okay, at the edge, then you feel it is harder to move that. So that's one concept of moment of inertia. So whenever you have this at the edge of that, of this pen, so what is actually the a moment of inertia? It is actually 1/3, okay, 1/3 of ml squared, which is much bigger than this one. So it is actually 4 times bigger, right? So if you convert that this to 12, okay, so you actually have 4 over 12. So this is 112. Okay, this is 412. So this it is actually 4 times bigger moment of inertia. Okay, if you put your hand, okay, at the edge of this pen, okay, so it will be reduced up to 4 times when it is at the center of this pen. Okay. Okay, similarly, if we have the, let's say, a rectangular plate, okay, we have the axis through the center. So whenever it is you are you are considering the axis of some object at the center, of course, you will be able to reduce the moment of inertia. Okay, so you will be able to reduce the moment of inertia of the object. Okay, so whenever you want to lift up the object, okay, whenever you want to lift up the object, so basically, if I have a book, uh, let's say I have a book here. Okay, so I have this book. Okay, whenever you lift it up, okay, at the, okay, you see my hand there. So it is at the center. It is much, you feel it much lighter, right? To move that. Okay. Compare if I put my hand at the edge. So you feel it's very, very heavy. Okay. To move that. Okay. Compare you put your hand at the center. So whenever, so the trick is whenever you want to move a heavy object, so try to leave it from the center of that object. Okay, because that actually reduce the moment of inertia for you to move the object. Okay. All right. So look back at the example. So for the rectangular plate, we have the I is 112 and okay, and then a squared plus b squared. Okay, a squared plus b squared. So that's the moment of inertia for the rectangular plate where the axis of rotation is at the center. But if we have the axis of rotation, if we have the axis of rotation, it is actually along the edge. It is along the edge. So now the axis is on that side. Okay. So if you are referring to again to this book, okay, so it is actually to that side. Okay, you want to move that. All right. So you want to move that. So that I is 1/3. Okay, 1/3 m a squared. Okay, 1/3 m a squared. All right. So that's the moment of inertia for the rectangular plate. Okay, now we have a cylinder. Okay, we have a cylinder. So we can have a hollow cylinder. Right? So we have a hole at the center of the cylinder, or we have a solid cylinder. So we don't have any hole. Okay, how about that? So which one having a bigger moment of inertia? Okay, so you can compare within those three. As you look there, so which one have the biggest moment of inertia? Of course, it is the solid one. As you can see that, it is the solid one. Uh, Sorry. Uh, yes, it is the one, right? It is the one. Okay, the moment of inertia, it is the one that has, okay, you look over here, this half mr, and then mr squared. So compared to these two, so which one has been? So this one. Okay, sorry about that. So when we have the cylinder that is hollow, right? So it is having much more. It is having much more moment of inertia. So let's say we want to roll that object. Okay, we want to roll that object. So as we look over here, okay, so we want to know which one will travel first. Okay, which one will travel first, and then of course it will have the less moment of inertia. Okay, so compared to these three, within these three, of course, the number one with the highest moment of inertia is this object. Okay, and the second one is this one, and the least moment of inertia belongs to the solid cylinder. Okay, let's look at this demonstration. Okay, this guy again.
This experiment, I have two food cans.
Give me a while. Okay, you have this guy again.
In this experiment, I have two food cans. One has milk, a liquid, and one has refried beans, pretty solid. What I'm going to do is I'm going to roll the cans down the ramp, and the question is, which can will reach the bottom first?
Okay, which one? As I just mentioned to you, either we have the refried beans, okay, will win. The milk beans will win. They will finish at the same time. Okay, which one? So, who choose A? You can raise your hand. So for A, anyone? With the fried beans, all right? Nobody. And how about B? With the milk bean. Sorry, with the milk inside the can. Also nobody. All right. How about the third one? They will finish at the same time. No response at all. Okay. Anyway, we will have quiz after this. All right. Okay. So the refried beans will win. So I will choose. I try to choose A. Okay. Let's have a look.
Let's find out. As you can see, the can of milk won. This is because the can of refried beans acts as a solid cylinder rolling down the ramp, while the can of milk acts as a hollow cylinder with the milk acting as a sliding mass. More energy was required to spin the can of refried beans than to spin the can of milk, and therefore the milk won.
Okay. So when in terms of speed, okay, it is actually all right. So you notice that uh, the milk can win, right? The milk can win. So the milk can is the hollow one, all right? Hollow one. So this one win, even though it have the largest moment of inertia over here. Okay, but when it started to move, all right? But when it started to move, then it is harder for you to stop that object. Okay, it is harder for you to stop that object. So that's why when it moves, then it will move faster, right? So because the energy has already changed, okay, the energy has already changed from the potential energy to the kinetic energy. Okay, so remember that. So whenever the object is traveling, okay, whenever the object is traveling, so the one that has the hollow, that is having the most hollowest cylinder will travel faster. Okay, so that's the concept. Okay, let's have a solid sphere, right? So let's have a solid sphere. So we have a solid sphere and thin wall hollow sphere. So as we can expect, of course, the hollow one will have the bigger moment of inertia, okay, compared to the solid sphere. Okay, so for this thin wall hollow sphere, we have 2/3, okay, 2/3 of mr squared, and then this one is 2/5 of mr squared. So this having the larger moment of inertia. So this one having a larger moment of inertia. Okay, so let's relate with the gravitational potential energy. Okay, all right. So if we have the gravitational potential energy of an extended object is same as if all the mass were concentrated at its center of mass. Okay, so let's say this athlete, okay, um, is jumping. Okay, this athlete is jumping. Then, okay, let's say the center of mass, okay, of Earth is actually, okay, where is it? Of course, it is somewhere over here. Okay, so it is somewhere over there. Okay, so we need to this jumper need to balance. All right, needs to balance. Okay, make sure that the center of that mass, okay, is actually should be, okay, should be at that area. Okay, should be at that area.
Doctor,
Yes.
doctor, sorry, are you sharing the screen now?
Okay.
Because I still see the video.
Oh, this guy. All right.
Yeah.
Okay, I'm going
Thank you,
to do that.
doctor.
Thank you. Okay, thank you, Alia, for that. All right. Okay. Okay, now you can see that. All right, so we have this jumper. All right, so the moment of, sorry, the center of the mass of this jumper is actually somewhere at the middle. Okay, so at the middle of this, of his her abdomen. All right. So this actually, when we have, uh, when this jumper put his her body at the center of, at the center of the mass of our body, then we can have, okay, the u gravity, so which is equals to the mgy. Okay, so we can have the highest, uh, the highest potential energy. Okay, so we can have the highest potential energy, okay, at that time. Okay, because it is actually when we put our body, okay, when we try to jump, right, when we try to jump, okay, like this one, okay, and then if we don't put ourselves, okay, if we don't put ourselves like this guy, so that's why you see the jumper is actually jump backwards. All right, jump backwards, okay, like this, jump backwards, like that. Okay, it won't use, okay, his body to jump on the other side, okay, on the straight side, okay, on the front side of the body. Because of what? Because what he wants to do is to make sure that the center, okay, the center of the body will be able to pass through the pole, okay, pass through the pole, okay, or the barrier, okay, or the barrier, at the certain height, because what you have that is the largest potential energy over there. Okay, so for example here, so the athlete arches her body so that her center of mass actually passes under the bar. Okay, okay, so you look at this body. So when it is like that, okay, the center, so the mass, okay, the center is over here. So the center of the mass, okay, so the center of this object, it is actually over here. Okay, so it is somewhere over there. Okay, so whenever she jumps like that, so this technique only requires a smaller increase in gravitational potential energy than straddling the bar. Okay, so it just having to just increase, okay, just increase that this center of the mass, okay, in order to pass through, okay, to pass through this bar, okay, in order to pass through that. Okay, so that's why it is important for the jumper to jump as high as possible, all right, as high as possible, so that they can push the center of mass to be higher than this bar. Okay, so if the center of mass it is higher than that bar, of course this jumper can pass easily the bar. Okay, all right. So we have another theorem where we call that as the parallel axis theorem. Okay, there is a simple relationship called the parallel axis theorem between the moment of inertia for an object about an axis through its center of mass, okay, and the moment of inertia about any other axis parallel to the original axis. So let's say we have this baseball bat, okay, we're having the mass of m, okay, and then we have rotation axis 1 through the center mass of the bat, okay. So the moment of inertia of this axis is ICM. Okay, and then we have the second rotation axis at 2 through point P, okay, is parallel to a distance D axis 1. Okay, so the moment of inertia of this axis is IP. Okay, okay, so of course we will put our hand, okay, over here, right? So we put our hand over here, so to pull the to pull the baseball bat, okay, to hit the ball, okay. So the moment of inertia that is calculated, okay, when we uh, trying to pull that baseball bat is calculated using this theorem, which is IP, okay, which is IP equals to ICM. So because it's center from here, so we need to calculate the moment of inertia over there plus md squared, okay, d squared of the distance. Okay, so that's about it. Okay, so that's about the moment of inertia for the baseball bat. Okay, so to calculate the moment of inertia, so that can be found by doing the integration of r squared pi dv. Okay. Okay, so let's say our planet, our Earth planet. Okay, so by measuring a small variation of the orbits of the satellite, okay, so we can measure the Earth moment of inertia. Okay, so by just measuring the small variation in the orbits of the satellite. Okay, so why the Earth having the moment of inertia? Because our Earth moves, all right? So when an object, of course, it will have the moment of inertia. Okay, so remember that moment only happen when the object is moving or is about to move, all right? So if the object is currently moving, of course, it has previously the moment of inertia. Okay, all right. So that's it for chapter 9. Okay, so as you have learned from chapter 9, so actually I'm trying to giving you more marks. So today we're going to have a game, right? So it's a simple quiz. So basically about this chapter, so there's actually no penalty, but whoever the, the top three, okay, get the top three will obtain the additional marks for your grade. Okay, so are you guys ready? I'm going to open that quiz, okay, in a few minutes. Okay, or do you guys want to have a break for a while? Are you guys there?
Yes, yes.
Yes.
Okay, so you want to have break or you just want to start with the quiz straight away? Or you want to have the break after the quiz?
Have a break first.
But then Munira, you want to answer the quiz first?
Have a break.
Okay, so let's have a break for 5 minutes. Okay, so we will continue again at 9:23. Okay, we will start again at 9:23 with the quiz. Okay, you guys ready? All right. So you could okay, look at the screen. So basically, you can go to joinmyquiz.com, okay, and then you enter the game code over here. All right, and I will see you over here, and then we can start. Okay, let's do it now. Okay, now is there. Who is? Because I need to record, okay, who will got the highest one. Okay, so you will get the marks after this. So tell me. Okay, now we have 7 of you. Okay, 9. Come on, guys. All right, 10. Okay, we have 11%. Come on. We have 20 students in this course. So the rest, please join as soon as possible because we're going to start soon. Okay, 12 of you. All right, 13 have joined. Okay, you guys don't want the additional marks. So for the rest of you, 7 of you, I will start within 1 minute. Okay, I will just wait for another 1 minute and then we will start. Okay, I will start within 10, 9, 8, 7, 6, 5, 3, 2, 1. have 10 seconds left. Okay. Go, Elia got the first position. All right. Next question. Okay, Alia and Ezrin. Okay. You guys ready for the next one? So Alia still leading the board. Okay. Balkis now is moving up. All right. So, okay. Some of you also use the vector rule. Okay, remember that the direction of angular velocity can be determined using the right hand rule. Okay, so you use the right hand rule. Okay, next question. So you have 30 seconds left. Okay. Okay, Kalian now got the third place. Wow. I get okay, 6 of you choose angular speed and 6 of you choose the moment of inertia and 6 of you choose the angular acceleration. Okay, so if either of you choose the angular speed or moment of inertia, that's correct. Okay, so it is not related to angular acceleration. So it is related to angular speed and moment of inertia. Okay, the last one, probably the last question. Okay, nobody still can challenge earlier. Okay, now Jai going down. All right. Okay. So that's the last question. Okay, so I got the first one, Kailiang second, and Azrin the third one. Okay. All right. So thank you for those who participating today. All right. As I mentioned, the top three, the top three will get additional marks for the course, right? Okay. So today we're going to start with our lab session, right? So basically, you can open up your lab manual now. So again, I congratulate Elia, okay, because she got the first. So we will have more games after probably next week as well. So hope you guys paying attention to what I taught during the class time, so you can gain additional mark for your grade. Okay. So
Thank you, Doctor.
okay, again, congrats. Thank you. All right. Okay, so we going to start with our lab 3. So with the lab 3, let me open up my file. Okay, this is the lab menu that I gave you yesterday, right? So for the learning outcome, so basically this experiment 3, we will look at on the rigid bodies, so which is the rotational dynamics. Okay, so what you will learn in this lab, so basically you will be able to explain the rotation of rigid bodies in terms of angular angular velocity and angular acceleration. Okay, and then you need to be able to calculate the moment of inertia of object of various shape, rotation axis. Okay, and third, analyze the relationship of and angular acceleration. Okay, and the fourth one, you should also report the moment of inertia about a rotation axis and the relationship with the rotational kinetic energy. Okay, so you have just learned that. Okay, and then last one, you should be able to analyze the conservation of angular momentum. Okay, even though they are changes in the object shape. So this angular momentum we have learned before in the chapter 8. Okay, so you have learned about the fundamental concept of moment of inertia, all right? Angular, and then you will also have the centripetal force, torque, and angular momentum. Okay, so the moment of inertia. So basically, in the general form, you can be written in terms of beta and r squared. Okay, so beta is constant. Okay, for example, in the rod you have 12, okay, 112, so that's beta. 112, 1/3, okay, so that's beta. And then you also have m, which is the mass, and r R is the distance from the axis of rotation. Okay, so basically you will have 4 experiments. So you have 4 experiments in this lab manual. So you open the following simulation. So you just straightly follow what the instruction on the lab manual. Okay, so it will be a straightforward one. Okay, so basically you will first one is rotational inertia and torque. Okay, you just press start. You just press start to run the simulation. So you can see that this is a bowling ball, okay, which is a solid sphere. Okay, you need to determine in which direction is the solid ball spinning. So you need to answer that. Okay, and then you need to repeat this question by changing over here. If you choose the spherical shell, if you choose the solid cylinder, and you choose the cylindrical shell. Okay, so you notice that when you have different object, so you basically having a different angular acceleration. Okay, you have different angular acceleration. Okay, so you need to answer the question number 4. So you need to observe yourself. Okay, and then if you change the radius, okay, you need to halve the radius. So right now the radius is 2. So for number 5, you need to change the radius to 1. Okay, you change to 1, and then what happens to the top? Okay, so this is your top over here. Okay, if you have the force, what happens to the top? So you make the radius back to 2, and then if force, say force now is 10, okay, and then what happens to the top? So you need to also mention that. Okay, choose the solid sphere. So you choose the solid sphere, and then with the given radius, mass, and force, okay, you need to determine what is the angular acceleration, and the acceleration of top, okay, equals to moment of inertia times angular acceleration to calculate the moment of inertia. Okay, so basically for the rest of that, it is similar, so just change that value. So that's about it for the experiment number 1. Okay, so for the experiment number 2, you are given, okay, this table, okay, where you have the top and alpha. So alpha is the angular acceleration. Plot that. So T, the top versus the alpha. Okay, you need to find out what is it, the graph linear, and then what is the slope, all right, and what are the units of the slope, and then what does the physical quantity does the slope represent. Okay, for example, the moment of inertia, or the angular velocity, right, or the mass. So you need to determine that. Okay, so that's about the experiment number 2. So up to now, are you guys clear?
Yes, doctor.
Okay, good. All right, so let's continue with experiment number 3. So for the experiment number 3, you need to observe the rotational kinetic energy. Okay, so you open up this simulation. Okay, and then it is the one that you just saw in the video. So we have, okay, let's say we have this solid sphere, and then we can also change that to the solid cylinder, or we can change that also to the thin cylindrical shell or thin spherical shell. So you can change that. Okay, so basically what you need to do is first to uncheck, okay, user defined solid object. Okay, and then select all of 4 of other boxes and then set the angle about 6 degrees. Okay, set the angle about 6 degrees. Okay, and then you have 4 objects and then you can run and then you see which object is bottom first. Okay, you see that. All right, so that's how the object travels. Okay, and then you need to answer the question number 3, and then 4, you need to select the solid sphere only. Okay, and then when you increase the mass, number 5, and when you decrease the mass on number 6, sorry, when you increase the radius on number 6, and then 7, you select back the user define. Okay, you define the moment of inertia and then set 2 different values, okay, for its moment of inertia. Okay, and you check which one will reach the bottom first. Okay, after that you just run the object. Okay, so you can change the value. Let's say you put 1 and then another one you put 4, for example, and then you observe that. Okay, so that's about the experiment number 3. Okay, for the experiment number 4, we have another simulation. Okay, so we have this angular momentum experiment. Okay, so for the angular momentum, so we have a person on the rotating platform. Okay, so for example, you are on the merry-go-round. Okay, on the merry-go-round. So we have a first situation. So what you need to do is just follow the instruction. So you keep the radius of cylinder 5 meter. Okay, that's 5, and radius of the person path is 2.05. Okay, so you see that. So the person is moved, okay, to the center or to the edge of the cylinder. So it's 2.5, 2.05, sorry. Okay, and then mass of the person. So you increase that mass. Okay, you see that the person get bigger. Okay, when you increase the mass, put that to 100. Okay, you can also change the value over here as well if you want. Okay, and then the mass of cylinder is 100. Okay, now you know that, okay, you have your omega over here, and then you have the centripetal force. So you need to determine what is your angular velocity. Okay, so the velocity is already given. Okay, the centripetal force is also given as well. So that's not the problem. Okay, so when you move the person towards the center of the cylinder, so we need to check what happens to the angular velocity. Okay, what happens to the moment of inertia? And then if the moment of inertia increases, what happens to the angular velocity? Okay, so just try to change that. And then for the second situation, it is also similar one. It's actually just change the values over there, right? And then for the situation C, also you change the value over here, right? And then you need to note that what's you observe for your lab report. Okay, so it should be a straightforward lab for this week. Okay, so remember that Thursday is a holiday, so we don't have a class on Thursday, right? So it will be, so we don't have a class. So we will meet again on next Monday. Okay, any questions so far? All right, so I would like to thank for those who already gave me the feedback. I really appreciate your feedback. Okay, so for those of you who haven't give the feedback, you can do so. The feedback will be closed until tomorrow's night, okay, at 11:59 p.m. So after that, you won't have the chance to increase your mark, okay. So for the feedback, you will obtain 1 mark, okay, from the out of 30. All right. So 1 mark out of 30, which will be top up to your test 1 result. Okay. All right. So you guys have any question?
So,
Yes, Kaliang, you have any question?
no.
Okay. By the meantime, also, I'm thinking of giving you extra exercise as well for you to do the practice. Okay, I'm going to give that with given with the answer. All right. So that one will give you also extra marks as well. So actually depends on the performance of you. So if you manage to answer all, so you get extra marks. Okay. Actually, there are a lot of questions. Okay, there are a lot of questions. So you can do that. So actually, it is a good one for you to prepare for your test and also exam later. Okay, because it is a problem solving question. So basically, if you have any concern about that, we can just let me know and then we can just discuss that during the class time as well. Okay, and all right, so that's it for today. So let's turn on your camera and take a picture together for attendance today. Okay, congrats to Azrin as well. So you got the 3rd place for today's game.
Thank you, Radha.
Okay, welcome. Okay, I'm going to count from 10. Okay, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, give me one more shot. Okay, thank you everyone. Okay, have a nice day. All right, and then I'll see you again next week on Monday. Okay, Assalamualaikum and bye-bye.
Thank you, Doctor.
Thank
You're
you.
welcome.
Thank you, Doctor.
Thank you, Doctor.
Welcome.
Thank you.